Now, another class of methods that we use for root finding is open methods. So what are the open methods? So basically they depend on the gradient or iterative schemes in order to find the values. So there may be different approaches, but here is the differences between the graphical methods and open methods. In bracketing methods, so basically we always continuously take the interval, and depending on the position of our new point, we choose one of the intervals and we continue like this until we reach the root. In case of a graphical method, so what we do is, in case of an open method, what we do is basically, as you see here, we choose an initial point. It can be any point, and then we move to our new point, which is the possible location for the root, and then we evaluate the function and whether we check whether the function is 0 or not there. And then if it is not 0, again we calculate we draw a straight line which crosses. We don't draw, but mathematically by using the analytical geometry you can easily calculate a line from that point. If you know the function, basically you can calculate the slope of the function at that point by calculating the derivative of it, and then you draw a straight line from that because you know the slope of the line and you know the point, and you try to reach to the root by successive iterations. In fact, it may have some drawbacks, as you see here. For example, your solution may be divergent. A small change in the initial guess, okay, so initial point, may cause a divergence. For example, here in this case the gradient is slope brings you to this point, and then you go here, and then you completely you are getting far away from the root step by step, which we call divergent. Again, open methods, in case of an open method, function has to be continuous. There shouldn't be any singularity in order to find the root. And in fact, if you have multiple roots, the point where you begin the calculations becomes important, and as we will see in the forthcoming slides, in fact, as a result you may reach to different roots depending on the initial guess or initial value. Now, first method within the class of open methods is fixed point iteration. Now just assume that we have a function f of x, okay, and we want to find the root of this f of x. In fact, what we do is we take out the x from this function f, and we write x is equal to some function g of x. As a result, in each iteration we arrive to a new value of the x, because we want to determine the location of the root, and then we calculate the relative approximate error. So xe plus minus xi divided by xi plus 1 multiplied by 100. So let's see the examples. Just assume that we have a simple polynomial here. Okay, so it is x squared minus 2x plus 3 is equal to 0, and certainly we have two roots because this is a second order polynomial. So what we do is very simple. We take out the x from here by putting it into the other side of the expression, then we reach to this equation, right? This expression. X is equal to x squared plus 3 divided by 2, because certainly this condition, this expression satisfies this condition. As a result, the x that we are going to find should be close to the 0. Now this is how we modify the function. What if it's very difficult to extract the x from the equation, as is the case here, for example finding the roots of sine x? So what we do in this case is you add both sides x, and then you put the initial guess here, sine x, and this will give us, so this is I plus 1 and this is I. So these are the values from the iteration I, and it will give us the value xi plus 1. If the result is getting closer to the 0, we say that it is converged. So this is basically the fixed point iteration. So let's see how the values are changing. For example, here we have a function e to the power minus x. This is our function. Sorry, just don't see this part. This is a mistake. This should be here. And then what we do is we take out this x, because this has to be equal to 0. And we take out this x and put it into the other side of the expression. As a result, we arrive at this expression. So we begin from an initial guess, and then we evaluate it. So we, after obtaining the xi plus 1, we substitute the xi plus 1 into xi and we get the new value. So we do it successively. So here are the values for the evaluation. For example, we begin from 0, and in the first iteration we reach to the value of 1. So x1 is equal to 1, and the error is 100, and the true error is 76.3 for this function. And in the second iteration it continues. It is the relative approximate error is 171.3, and the true error is 35.1 by means of percentage, and it goes like this, and at the end you reach to a very small value of xi, which is 564,879. So the relative approximate error for this 10th iteration is 1.11, and the true error is 0.4%. Of course, there is another technique which is called two-curve graphical method. It helps us in understanding the convergence properties of the fixed point iteration. So this is why we will have a look at it. Just assume that we have a function and it crosses the x-axis at a certain point, so which will give us the root of the function. Now we decompose the function into two parts, as is the case in the fixed point iteration, and now f1x is equal to x and f2x is equal to e to the power minus x. Now we draw the line both functions, and we look at the point of intersection. Now the x coordinate will give us the root of f of x in this case. Of course, this helps us in understanding the convergence of the fixed point iteration, so let's have a look. Now let's see here. Now this is convergent. You see, we begin from x0. We first evaluate the function g. At that point it has to be equal to, this is y2, so y2 is equal to y1, right? And then it gives us the x value. Now for the corresponding x value, which is x1, we evaluate the g of x again, which gives us the second y value, and then we go to the x2, and as you see, in each step we are getting closer to the root. Okay, so this is one example. And of course, if you look at this function, now the slope of the g is smaller than 1. You see, because this is the slope, y1x has a slope of 1. Therefore, in this region, it is smaller than 1. So let's look at this function. So again, we begin from a point x0, and we find the y2 for the corresponding x0. Since y1 has to be equal to y2, we can easily find the new x value. So y1 is equal to x. We find the new x value, and from this x value we find the new g value, and each step we are getting closer and closer to the root. In fact, if you look at here, the slope is negative. We will see why it is like this. But again, if you draw a line perpendicular to the y1 is equal to x, you see that the slope is the absolute value of the slope is smaller than 1. So let's see. Now we have a different function y2 g of x. Of course, in this part of the function, or in general, the slope of the g is greater than 1, because y1x has a slope of 1. And then look what happens. We begin from a point and we calculate the y2, and we go to the y1x, and then our new point, and then our new point on the y1x, and as you see, we are getting away from the root. Now here we have another function. We begin again from an arbitrary point x0, and the first thing that we do is we evaluate the g of x. So this is our point. Then we go like this, we go like this, we go like this, we go like this, and as a result you are getting far away from the root. Now the slope is, if you look at the slope of g of x, you see that the absolute value is larger than 1, and as a result we say that convergence of fixed point iteration occurs only if absolute value of the slope of g of x, derivative of the g of x, is smaller than 1. Now let's look at the algorithm for fixed point iteration. So first thing that we do is we first create a root. Of course, initially our initial guess is the root xr. Then we have a dummy variable iteration, iter. So we assign the current value of x root to the previous value of the xr, x root, and then we calculate the g of x and find the xr. We increase the iteration number with 1 and we check whether the root is found. If xr is not equal to 0, certainly this means that there is an error, and we calculate the relative approximate error, and if error is smaller than error threshold or iteration is bigger than maximum limiting iteration, we say the code exit and we find the root. So this is the algorithm for fixed point iteration. Okay, now well, we have seen the theory related with the fixed point iteration. Now let's write a simple script in MATLAB. So let me remind you how we did it. So it is we have the function which we want to find the roots of it, and we begin from an initial point. Of course, we just take out the x out of this function and we rewrite the whole function again. So as x equal to some function of x, and we put the initial guess on the right hand side and we get the new approximation or new guess for the root, and we do it until it converts to a certain value, until x converts to a certain value. Of course, in some cases it may be difficult to do that, so in such a case we add x to the both sides and then we evaluate it. Okay, so this is one thing, and let me continue with the false position script again. Instead of, now it is fixed point. Iteration. I changed the name of the script. And again I will save it with this name, just for simplification. Now I will continue with the same function, but the point is now I have to add. So remember my function. It is very difficult for me to extract x from this function. So as a result, what I do is I put x here. Now I change the function as my function 2, the name of the function as my function 2, and I will save it as well. Okay, so basically I add x to the both sides. Okay, now I have an initial guess. Now I don't need the bounds anymore, but maybe it's better to put clear all and close all. Okay, again I may need to cancel the iteration at a certain value. I don't need to evaluate the functions anymore here. XR previous, I don't need it as well. Okay, now again I will use the conditional statement while command. Index is equal to index plus 1, but now here I have another thing. So new root will come from the initial guess. So I will, or let me write it like this. This is my function 2 XR. So XR is let's write here XR previous is equal to XR, and let's begin with the XR previous or XR. We can begin from some value between 20 and 4, so remember that this was the interval that we are looking for, and let's say that we begin from 20. So my initial XR is 20. This is XR. So I will delete this line because there will be then a problem because of this line. I will talk about it. Now I have new XR value. I have the EA root value will be XR. I don't need to evaluate the function anymore, and I don't need all these lines. Okay. Let me take this line here from, so I have my error here. Okay, I have my next new value for the XR. Okay, and then the error will be calculated. Let's check this simple script. So remember how the loop was. We begin with an initial approximation of the root. We give an initial value to the error which is greater than the bound. Yes, we have a maximum iteration, and as soon as this condition is satisfied, this will be done. So we increase the index with 1, we assign x previous to the XR, then we calculate the XR, then we check the error, relative approximate percentage error, and then it seems to be okay. And let's see how it will work. My function 2XR, that's okay. Now let me run it. Wow. It converts, but you see the value is highly oscillatory here for this function, for the same function. And even if we reach to 100, let's check the value then. 14.81, 8176 for this complicated function. So we are still far away from the error, and let's check the relative percentage error. So what's the value is? As you see, after 100 iterations, the error is somewhere higher than 0.1%. .22. So it is not very efficient for this function. Okay. Well, let's run it again, and let me check whether I can change the line properties, because I want to make it more visible to you. Now I'm using the default values. I don't need it. I don't need that. So here, maybe property editor. Here it is. Okay, so inside the property editor menu, let's enlarge this, and then I change the color. Okay, whether I can change the line thickness. Because I want to change the line thickness. Line, plot type, line. There are more properties. I want to increase the thickness. Yes, here it is. I want to increase the line width, and I want to make it 2. Yes. Now I can close it. I don't need it anymore. So these are the values that I have after 100 iterations. Now I will close this figure. Also I will close the other one. Now what I'm going to do is I will increase it to 1000, and let's see how many iterations will it take, or let's say 10,000 iterations to go below the error threshold. Okay, here it comes. Now we reach to the error threshold. Again, we go to the property editor from the menu. Now I learn it. I will go to the more properties. I want to increase the line width. Let's say that this is sorry, it's a little bit slow here. Okay, let's remain it like this, so it doesn't matter. I will do it from the command line then. Now these are the values as you see, and the final iteration is like 340 approximately. Okay, so this is my maximum iteration count. Now let's check the error. Now we already reached to the error threshold 10 to the power minus 4, and the value here is, again, you see 333, so this is somewhere 340 iterations for it to decrease below the error threshold that we give. And this is much higher than the one that we have seen in the false position method for this function. Okay,